Okay, today we will discuss virtual private networks, and specifically our objectives for today are to explain the basic concepts behind virtual private networks and describe some of the more technical capabilities behind them, including encapsulation and encryption, authentication, something called ESP, something called layer 2 tunneling protocol, point-to-point tunneling protocol, IPSec, internet key exchange, and lots of other goodies. Okay, virtual private networks. Let's think a little bit back to 4663 when we discussed the CIA triad. That's not Central Intelligence Agency, but the tenets of computer security and information security, and the C stood for confidentiality, and the I for integrity, and the A for availability. Well, VPN allows us to actually, within the network infrastructure, to create packets and communications that are confidential, that are available, and that also ensure the integrity of the packets. And essentially what a virtual private network does is enable computers to communicate securely over insecure channels. And if we think of the most insecure channel there is, it is the internet. Because unless specified, nothing is encrypted when it goes over the internet. It goes in clear text. So what a virtual private network does is take that insecure channel and allows us to secure the packets in ways that makes them confidential and makes them so that we know whether somebody has modified the packets or not. So essentially it allows us to exchange private encrypted message that others cannot decipher. So the VPN can be broken down into its constituent components. The first it's a virtual network connection. One of the ways to ensure that somebody can't listen in on your connections is to have a leased line. And a leased line means that you're paying a lot of money and you've got your own line that's connected from one point to another. The problem with this is that they're extremely expensive. Another thing we can do then is to use certain types of technologies to run the same packets over an insecure channel, a non-leased line, such as the internet. We can do it for a lot cheaper, but we have to come up with the right technologies to ensure that our communications are secure. So essentially what a VPN does, it uses the internet, an insecure channel, to establish a secure connection through a secure tunnel. And by doing this, what you're doing is you're extending your organization's network. So physically we know that within a network that if we have secure boundaries, that somebody is unable to listen in on our communications within a network. However, if we want to extend our communications outside of the network, people are able to listen in over the internet. However, if we use a VPN, this is not the case. So we have the virtual network connection, and we also have endpoints. And the endpoints can be within an organization or within an organization to another organization. And these endpoints are specified computers, users, and or network gateways. And we'll actually show a little graphic of this to make it a little more clear later on, like right now. So what we have here is we have the internet, which is by definition insecure. It's not everything that crosses the internet is not encrypted. Here we have our main office. We have a branch office over here for organization, and then we may have business partners over here, and we may even have a client site. And what we want to do is we want to be able to share communications between these four different sites through the internet. Well, one thing that a VPN does is it allows us to take the communications that we create through one of these endpoints and to send it through a VPN gateway, which then typically may encrypt or do something else to the packet, which is then sent through the internet, the insecure channel, to, let's say, the branch office, whereupon it meets the VPN gateway, which is then, the packet is decrypted and then delivered in clear text to the recipient somewhere over here. So why would one want to establish a VPN? Well, there's a lot of business incentives driving the VPN adoption. The first is as opposed to a lease line, which can run thousands of dollars a month. The VPNs are very cost effective because we're already using the infrastructure of the internet, and all we have to do is buy either hardware or software to create the VPN connections. VPNs also provide secure communication between remote users, such as contractors, traveling employees, partners, and suppliers. Whether you know it or not, one of the big problems in industry is industrial espionage, and companies want to get a leg up, so one of the ways they can do this is do things that are illegal, such as listening in on other people's telephone communications, conversations, and probably most easily is to sniff the packets going across the internet. What a VPN does is provides that secure communications so that it would be nigh on impossible to do this. It's not that it's impossible if the VPN is not set up correctly. However, if it is set up correctly, it really is nearly impossible to sniff these communications. Other VPN components. We're going to have a VPN server or host, which is configured to accept connections from clients, and then we have the VPN client, which is the endpoint connecting to a virtual private network. So essentially what we're having is as we saw on the previous page, is that we have a guest that's, or VPN client, that's actually creating the communications. This is sent to the server, which then will may do one of a few things, but typically they will encrypt that information. As we'll see later on, you can encrypt several different things, or you can obfuscate several different things, including the IP address of the sender. And then this then will communicate with a VPN server, let's say over here, which then understands the protocol that's being used, which then again is the message is decrypted and then sent on to the recipient over here. Other VPN components. We have the actual tunnel, and the tunnel is the connection through which the data is sent. This is the secure tunnel, and as typically it will not be in clear text, but as we'll see later on with IP security and internet key exchange, that you can actually send something securely, so it may not be confidential, but at least we'll know that if somebody changed the data within it, we'll be able to ferret that out. Then you have numerous VPN protocols. If you VPN to school, you know that if you have to get onto a server that's located on school, and you are outside of the UCF domain, that you have to VPN to school to do that. And there's a couple of different protocols that they use to do that, one of which is IPSec, and I believe the other is layer 2 tunneling protocols. We'll talk a little bit about that later. What a protocol is rules for communications. That is, it's a sense of standardized communication settings that both endpoints must understand and agree upon in order to create that VPN tunnel. And so the protocol is used to decrypt the data that's sent along the VPN, and it's also used to decrypt the data. And then of course you can also have types of VPNs. You can have a site-to-site VPN, that is a gateway-to-gateway, or client-to-site VPN, which allows rote access VPN. And so some client-to-site VPN would be great for someone who is either working from home or is traveling and needs to communicate with servers back home at their home organization, whereas the gateway-to-gateway is actually connecting two or more organizations. There are various types of VPNs in terms of either being a dedicated hardware VPN and software VPNs. and they differ in a lot of different ways. The hardware VPNs are going to be dedicated machines that are used to create virtual private networks, and they connect one gateway to another, and then the routers at each network gateway can encrypt and decrypt the packets. And you also have things called dedicated VPN appliances, which are designed to serve as an endpoint for a virtual private network. And the benefits of hardware VPNs is that they're scalable, is that you're able to add more and more VPN connections without a tremendous reduction in the throughput, and also they provide it says better security, but that's not necessarily the case. Because a VPN has a lot of the configurations preset as opposed to some software configurations. Perhaps that's what they're talking about here. And here's what we're seeing. We have two VPN appliances, and these are made by several companies. If you want to Google for that, Cisco makes really good appliances. In fact, we're using some of those for research over here. Here we have your organization. This could be an organization, or it could be multiple organizations, but you have your VPN appliance. Somebody creates a communication over here. It's sent through the VPN appliance. It could be encrypted. It sends over the VPN tunnel over here. It's decrypted, and then it's forwarded on to the recipient over here. And here's some of the different appliances and the companies that make them. We see the only ones with which I'm really familiar are some of the Cisco systems over here. This is what we're using. And you're free to take a look at those later on. Okay, then we have software VPNs, which of course are going to be a lot cheaper. They're really going to be easier to update, and these are often integrated with firewalls. And they're appropriate when participating networks use different types of routers and firewalls. Over here, whoops, if you're going from one company to another, typically they have to have the same, these VPN appliances have to have the same protocols available. So if you're using different VPN appliances and they don't understand the same protocols, they won't be able to communicate with one another. So you have that limitation there. However, when you're using different routers and firewalls, then a VPN appliance software base may be the better appropriate solution. The benefits are it's more cost effective and it offers maximum flexibility because you can use different routers and firewalls and the different endpoints. And here's some of the software VPN products. You have Checkpoint, which is a very well-known Israeli company. Netgear, 3Com, Symantec, and so on. So why would we use a VPN? There's several reasons, including being able to combine VPN hardware with software adds layers of network security. Remember in 4663 we talked about defense in depth. You have multiple layers of security, so if somebody breaks into the first layer, we have an added layer beneath that, and just makes the black hat's job harder to try to break into our resources. Or you can have one useful combination is a VPN bundled with a firewall, and of course you'll always want a firewall. However, VPNs do not eliminate the need for firewalls, because firewalls are at the boundaries and they allow us to determine what types of packets get in and what types of packets get out, and VPNs don't offer that capability. And of course they also provide flexibility and versatility because, as we'll see a little later on, is we can define various layers of protection, including some things which we may encrypt, some things which we may not, but we may have a checksum on each packet to determine whether something has changed or not. So some of the things you need to determine when you're selecting a VPN for an organization or yourself is to determine the compatibility. Are you going to be working with other organizations that already have VPN software. If it needs to be compatible, then your choices will be limited. Scalability, if you may need to add more and more clients to the VPN, you need to select a VPN solution that's scalable so that the throughput isn't reduced when you add more and more clients. The security level, that is, do you need something that includes a high level of encryption or not, or are you just concerned with the integrity of the packets? The cost, once again, the cost is going to be more for the hardware than the software solutions. And in fact, some of these solutions are free, including OpenVPN. If you Google for OpenVPN, one word, you'll see that there's solutions available that are open source. And also vendor support. If you need vendors to support, you need to look at their track record to determine how well the support is provided. Because if your VPN goes down, your VPN gateway, your VPN appliance goes down, you certainly don't want people to still try to log in and to communicate in clear text across the internet if you're sending sensitive communications. So what is the core activity of a virtual private network? It's something called encapsulation. And encapsulation actually includes three different things. As we'll see, encapsulation may well be combined with both encryption and authentication. And the authentication serves several purposes. We know what encryption does, but authentication determines the source of the packet, which is not something that encryption provides. So encapsulation, what that does is encloses a packet within another packet that has a different IP source and destination. And what this does is it protects the integrity of the data because it also includes a checksum, as we'll see shortly. So we see here that the originating computer has a 10-dot-based IP address, and this is going to be one of the reserved private addresses. We see here at some point in time we can encrypt the data. Recall that this is not necessary for creating a VPN. It often is encrypted, the data is encrypted, but not necessarily. But notice here at some point in time that this packet is encapsulated, so the source, here's the original packet, and then it's encapsulated within another packet, and notice that the source address has changed. So rather than going back directly to one of these computers, it goes back to the VPN router. What the VPN router does is then strips off this encapsulated header and looks at the actual source IP, and then this router would then forward on this connection to here. So what essentially it does is this encapsulation hides the originating computer's IP address. Now let's look at some of the tunneling protocols that are available. One of the older ones is called point-to-point tunneling protocol, and I think that's available within Microsoft Windows. And it's used when you need to dial into a server that has a modem connection. It's very good for using when you need to dial in from a computer with an older OS version such as Windows 95 or 98. And what PPTP does is it encapsulates the TCP/IP packets as we saw before, so that the header contains only information needed to route the data from the VPN client to the server. And it also uses something called MPPE, which is Microsoft Point-to-Point Encryption. And the encryption available for that is the RSA-RC4 algorithm. And so MPPE encrypts data that passes between the remote computer and the remote access computer. Later on, Cisco got together with some other organizations, I believe IBM off the top of my head, and actually created a version of a tunneling protocol called Layer 2 Tunneling Protocol, which uses the IPSec encryption standard. which is more secure and it's widely supported, and it's not really proprietary to Microsoft. So this is IPSec is actually an international standard as opposed to Microsoft's version of the encryption. And so the Layer 2 tunneling protocol, or it's also called L2TP, provides better security through IP security as opposed to MPPE, and we'll discuss what IPSec is shortly. And IPSec enables Layer 2 tunneling protocol to perform authentication of the information, encapsulation, as we saw previously, and encryption. And as we'll see shortly with IPSec, how authentication and encryption come into play and how they can be exclusive of one another. And so if you want to look at some of the modern operating systems and what they support, as you notice that point-to-point protocol is supported all the way back through Windows 95, but for backwards compatibility, even the more modern operating systems, XP and Red Hat and Linux, also support this. However, Layer 2 tunneling protocol was not in existence up through the creation of NT4, so you can only use Layer 2 tunneling protocol with the more modern operating systems, including 2000 XP, Red Hat Linux, and pretty much every other operating system that's come out. Okay, other tunneling protocols, and these are really not VPN solutions. But what they do is they provide solutions that are VPN-like, let's say. One of these is called Secure Shell, and you should have, if you've been in 4663, you should have used this. Secure Shell is actually a protocol that's open, and it's freely available. Open SSH. It was created by the folks from OpenBSD and still actively used and developed. And SSH provides authentication and encryption, and essentially what it is it's a secure replacement for Telnet. And so you can use it to create encrypted tunnels across the internet. It works with Unix-based and Windows-based systems. If what we'll see in your next assignment is that you can use either the SSH that comes with Linux, or you can use PuTTY, P-U-T-T-Y, which is the SSH application that's available for Windows. And it uses, as we discussed recently, public key cryptography. And so if you need to refer back to the previous iClass, you can do that. Then we also have SOX version 5, which provides proxy services for applications that do not usually support proxying. And if you need more information on that, why don't you you can Google SOX, so we're not going to go too much into that. Okay, let's talk about IPSec and Internet Key Exchange. Internet Protocol Security, IPSec, is a set of standards procedures that were developed by the Internet Engineering Task Force. And essentially, it provides for secure communications over the Internet, and it provides for three things. It provides for encapsulation of packets, it provides for authentication of the packets, and it provides for encryption. And the characteristics is that it works at layer 3, the network layer, so you can encrypt an entire TCP/IP packet, which means you can encrypt the header, which contains the destination address and port, and the source address and port, as well as the data. And it was originally developed for use with IP version 6, but they've actually made it backward compatible, so it also works with IP version 4. And it provides authentication of source and destination computers, as well as encryption. One of the great things about it is it's widely supported, is that almost all VPN solutions now provide for IPSec with Internet Key Exchange. And one of the key concepts behind IPSec is something called a security association. And what the security association is it's a relationship between two or more entities or endpoints. And what that is it is a security association describes how they will use security services to communicate with each other. So if you think about two people from different countries communicating. Let's say one person knows Spanish and French and the other knows English and Spanish. Well, if they're going to communicate with one another, they wouldn't be communicating one with French and English, but they would decide at some point that, well, let's communicate in Spanish because that's what we have in common. And that's roughly an analogy to what we see with the security association, is that the two endpoints must identify what they want to use to securely communicate, or that is, they need to agree upon what they want to use. And so the Security Association is used by IPSec to track all the particulars of a communications session, and they're unidirectional. That is, there's going to be two security associations set up, one from A to B and the other from B to A. Okay, the components of IPSec include the Internet Security Association Key Management Protocol, which is used for managing keys, and there's the Internet Key Exchange. Okay, somebody knocked on my door now. I can't remember where I was. Okay, Internet Security Association Key Management Protocol is related to IPSec and enables two computers to agree on security settings and establish a security association so that they can then exchange keys using Internet Key Exchange. And this enables two computers to establish an IPSec connection to exchange keys to make a security association. And IKE uses UDP port 500 on both the client and the server computers. Oakley enables IPSec to use the Diffie-Hellman encryption algorithm to create keys. The IPSec security policy management only runs on Windows computers, and it retrieves IPSec security settings from the Active Directory and applies them to computers in the domain that use IPSec. And finally, there's the IPSec driver, which is software that handles the actual task of encrypting, authenticating, decrypting, and checking the packets. Now, there are two IPSec core components. There's authentication header, and it's always abbreviated AH, and there's the encapsulation security payload, which is ESP. And so, authentication header provides authentication of TCP/IP packets to ensure data integrity within the packets. And this is done because packets are signed with a block of encoded data called a data signature, which is something we discussed recently. And the signature indicates to other IPSec compliant devices that a packet contains an accurate IP header information because it originated from a computer using IPSec. And so digitally signing a packet indicates that it hasn't been tampered with or that the IP information in the header hasn't been spoofed. So realize that it provides integrity, but it doesn't ensure confidentiality because nothing is encrypted. And now, within authentication header, there are two separate modes. You can use tunnel mode or you can use transport mode. So in tunnel mode, AH authenticates the entire original header and builds a new IP header placed at the front of the packet. So the only fields that are not authenticated by AH in tunnel mode are the fields in the new IP header that can change in transit. In transport mode, AH authenticates the data payload and the original IP header except the fields that change in transit. Let's take a look at this. Authenticated header message exchange. So here we have our data, and then we have the authentication header, which is essentially a message digest of the IP header. And so the data and the IP header, typically the IP header and the data are above one another, but the authentication header is placed between those two and sent across from router A to B. When it's received at router B, you can check the authentication of the IP header using the authentication header. Essentially, this is the digital signature that determines whether the IP header has been changed or not. Now if we look at the difference between tunnel and transport modes, here we have the IP header and the data, the original IP packet. In transport mode, this is what we saw on the previous screen. Notice that the authenticated, everything is authenticated except the fields that are changed in transit. However, with tunnel mode, authenticated the entire packet except the fields that in new IP header that are changed in transit, which would be this right here. Okay, encapsulated security payload provides for confidentiality for messages, so you're probably going to think that encryption involved, and yes it is. And so what ESP does is it encrypts different parts of a packet. And once again, it can be used in both tunnel and transport mode. Now in tunnel mode, ESP encrypts both the header and the data parts of each packet, and this encryption protects data, but because the IP header is encrypted, the data can't pass through a firewall that uses network address translation. The data won't pass because the firewall doesn't know how to interpret the IP source and destination information in its encrypted form, of course. Now in transport mode, only the data portion of the packet is encrypted. So as a result, if the VPN is to be used with a firewall that performs NAT, IPSec should be configured to work in transport mode. And we'll take a look at this right here. Here once again we have the original IP datagram. And notice now we're using ESP authentication. And so now we have an ESP header, and notice the data in its ESP trailer are encrypted, and then all of this is then authenticated, and it's placed at the back of the header, and then a new header is placed on the beginning of the packet. In tunnel mode, we see we have now that the IP header, the data, and the trailer are encrypted, and then the authentication is for the ESP header all the way back to the ESP trailer, and this authentication information is placed at the back of the packet, and then a new IP header is created. Now we see that network address translation won't work because it has to have access to this IP header, and instead a new IP header is placed on the start of the packet. So once again, if we're going to be using network address translation, you would have to use ESP in transport mode, not tunnel mode. Okay, encryption. We've already talked about encryption. Of course, encryption is the process of rendering information unreadable by all but the intended recipient. And within this framework, now we're talking about public key encryption. And so recall that one of the components is two set of keys, a public and a private key. But there's also things called that we might use called a digital certificate and a certificate authority. And the different key exchange methods include symmetric cryptography, which of course is single key encryption, just using a single key for both encryption and decryption. We have asymmetric cryptography, which uses a public and a private key. We also have internet key exchange. An internet key exchange uses the tunnel method encryption to encrypt both the header and the data parts of a packet and encapsulate the packet within a new packet that has a different header. And finally there's FWZ, which is a proprietary protocol that was developed by Checkpoint Software. Okay, a picture is worth 1,000 words. And so what we're seeing here is the use of IPSec with Internet Key Exchange along with the Certificate Authority. Recall that Certificate Authority are ones that, that verify the trust of a particular key, and so they sign the keys to ensure their authenticity. And then and so what certificate authorities do is they create digital certificates for these keys. And here we see that if the main office wants to communicate with the branch office, is that they first need to set up a security association, and there'll be one going this way, one going this way, and so that they agree on the protocols to be used. And when they're exchanging the keys, then they need to make sure that those keys are actually the verified keys. And so there's a certificate that's been created, which is a digital signature of each key. And then the digital signature can be checked by going to the certificate authority, which verifies the goodness, for lack of a better word right now, of the keys. And then once that's set up, then they can start communicating using public key cryptography. Okay, another version of encryption that can be used is called triple DES. That's the 3 DES. That's the way it's pronounced. So if you ever see that, it's triple DES, not 3 DES. And the data encryption standard was came out in 1976, and for many years, up until 2000 or 2001, it was the standard encryption protocol for all government encryption standards. And later on, it's been replaced by the advanced encryption standard. It was 56-bit encryption. It was a symmetric encryption. And triple DES is just a modification of DES so that it's used more than once. And it's not, and so it uses several different keys, and it makes it a lot stronger. It doesn't make it 3 times as strong as original DES, but just about twice as strong. DES is no longer used because it's really not secure. They've been able to actually break the encryption using a distributed attack on the key space. Triple DES is a lot more secure because there's 3 separate 64-bit keys to process the data. And usually in triple DES, you use the 3 keys, and you either, if I'm remembering correctly, you can use, you can encrypt with one key, decrypt with another key, and encrypt again. And there's other variations of that. Realize that triple DES requires more computer resources than DES, and of course it's going to be a lot slower because you're using DES 3 different times. And here's example. Actually, yeah, you have the clear text, and then you take the DES. The 60 is actually 64-bit encryption because 8 bits of that are parity bits. So 64-bit key encrypts the data. You take a second key and decrypt the data. And so obviously the decrypted data is not going to be the same as this. And then you use a third key to encrypt the data again. And then you have your ciphertext. Also, secure socket layers was developed by Netscape Communications a while back. And it enables web servers and browsers to exchange encrypted information. And it uses asymmetric encryption, public and private key encryption, as well as the socket methods of communications. And it operates at the network layer of the OSI model. And whenever you see HTTPS being used, and you see that key, depending upon what kind of browser you use, if you see the key in the bottom right-hand corner, that indicates that that you're using HTTPS and secure sockets layer. And it's widely used on the web, but it's unlikely to replace IPSec. Okay. Secure socket layers work thusly. First step is the clients connect to a web server using the SSL protocol, HTTPS, and then the 2 machines arrange a handshake process. So the client sends its preferences for encryption method, the SSL version number, and a randomly generated number. Now what does that sound like? It sounds like they're setting up a security association, because they're trying to agree on what type of encryption method they're going to use. Second, the server responds with the SSL version number, its own cipher preferences, and its digital certificate. And that digital certificate does what? It indicates that whatever key is going to be used can be verified from a certificate authority. And the client verifies the date and other information on the digital signature. Essentially what the client does, it generates and sends a pre-master code. And the pre-master code is sent to the server using the server's public key. Next, the server uses its private key to decode the pre-master code. It then generates a master secret key, and the client and server use it to generate session keys. And of course, the session keys are just that. There are keys that are used for a single session, and they're symmetric. That is, you don't have a public and private session key. You only have a single session key. Then the server and client exchange messages saying the handshake is completed, and then the secure socket layer session can begin. Okay, and so that ends this overview of virtual private networks. Very shortly, you will have an assignment that should be fun. It's not overly complicated, but it'll give you a good idea about setting up secure communications. You know, and unfortunately, this is there's no way we can actually set up VPNs. I mean, you can set up a VPN to, if you haven't already, to access computers online. You know, through the VPN appliance that we have here on campus, but that's very trivial and really doesn't teach you anything. And hopefully, you already know how to do that. We're trying to get down into more meatier issues in actually setting up things by hand. So that's essentially what we'll have to do for this, is do something that's that is not as substantive as what we would do if we had a lab where we could all sit down and create a network and create different types of VPNs, software VPNs. And the primary reason is I can't come up with a single assignment that would probably meet the demands that I could place on each of your computers, because each of you is using a different type of computer and different types of software and so on. So anyway, in lieu of that, we'll give you something fun to do and something where you'll learn something.